Section 4.7, Counting. We've learned various ways to set up and find probabilities based on varying situations. In some scenarios, it may be necessary to determine how many elements make up the sample space or event before we can compute the probabilities. And that's where counting comes in, knowing how to count up the number of ways something occurs. So we're going to start with a very basic concept to introduce the counting rule. Example 1. Suppose you have 3 different shirts, white, gray, and red, along with 2 different pairs of pants, blue and khaki, that could all coordinate together, meaning any of the shirts could be paired with any of the pants. How many different outfits could you put together? Well, you could have the white top with the blue pants, the gray top with the blue pants, or the red top with the blue pants. You could also have the white top with the khaki pants, the gray top with the khaki pants, and the red top with the khaki pants. So when we list it out, we notice that there are a total of 6 different outfits. Instead of listing out the entire sample space, we could obtain this number by, what do you think? There were 3 shirts and 2 pants. Well, we could have quickly gotten that 6 just by multiplying the number of shirts with the number of pants. This leads to the fundamental counting rule. If event 1 can occur m ways and event 2 can occur n ways, then the total number of ways the events can occur together is given by m times n. So, of course, this rule can be extended to 3 or more events. So if I had maybe a pair of shoes of varying colors to pair, I could multiply the different types of shirts I had, the number of pants I had, and the number of pair of shoes, and I'd get the number of arrangements I could make. Let's try that with a different example. Example 2. A deli offers a lunch special where customers can choose a ham, turkey, or roast beef sandwich, soup or salad as a side, and tea, coffee, bottled water, or a soft drink as a beverage. How many different lunch specials can be ordered? Okay, so for our sandwich, we have 3 choices, ham, turkey, or roast beef. So that's the first event. For our side, we have 2 choices, a soup or a salad. So that's our second event. And then for a beverage, we have tea, coffee, bottled water, or a soft drink. And we're not going to make the distinction between, say, Coke and Diet Coke and root beer, just that soft drinks all get lumped together. So among tea, coffee, bottled water, and a soft drink, that's the 4th event, and there's 4 choices. And when I multiply that all together, I get 24. So there's 24 different lunch specials. Example 3. For a new security system, employees are asked to select a 10-digit numerical code where repeating digits are allowed. How many possible codes are there? Sometimes with a problem like this, I'd like to think of it as slots or places. So I have 10 different slots that I have to fill up. Now I'm asking myself, just like with the previous example, with the sandwiches and the sides and the beverage, how many choices do I have for each slot? Well, there's 10 numerical digits, 0 through 9, so I have 10 choices in that first slot. But because I can repeat a digit, I also have 10 choices for the second slot, and so on for each slot. So that means since I'm multiplying all of my choices, the number of codes that there would be is 10 to the 10th power, which is a really large number. 10 zeros, so 10 billion. So lots of different codes there. Okay, so kind of similar to that in example 4. This time we're still going to have a 10-digit code, but we cannot repeat the values. So that changes things a little bit. Well, I'm going to still put my slots here. So again, I'm thinking about, well, what are my choices? For that first slot, I have 10 numbers I can choose from, 0 through 9. Now I pick something for that slot, and I can't use it again. That means for the next slot, I only have 9 choices. Well, now for the third slot, I can't use the first 2 numbers that were picked for slot 1 and slot 2, so now I only have 8 choices. And if I continue that pattern, I have one less choice every time. That takes me down to 1. So this time, instead of 10 to the 10th, it's 10 times 9 times 8 and so on. Which gives us 3,628,000. So fewer codes than what we got in example 3. Well, in example 4, notice that we had a pattern of multiplying whole numbers all the way down to 1. And this is called a factorial. So because the numbers went in order, 10, 9, 8, 7, 6, and I was multiplying them all together, that's called a factorial. So more formally, factorial notation, the number of ways n distinct items can be arranged is given by n factorial. So that exclamation mark that you see is just read factorial. This is a product of descending integers in the form n times n minus 1 times n minus 2 all the way down to the number 1. So just as we saw 10 times 9 times 8 times 7, or if I had 12 factorial, I would go 12 times 11 times 10 all the way down by 1, all the way down to 1. Be careful though, if you ever encounter 0 factorial, it's equal to 1. And that seems a little odd, but you'll just have to trust me. Okay. So let's just practice evaluating factorials. And I'll show you how to do this in your calculator. Okay, so for A we have 6 factorial. And if you were to just do it knowing that we just multiplied descending integers, that would be 6 times 5 times 4 times 3 times 2 times 1, which gives us 720. But your calculator actually has that exclamation mark or that factorial on it. So what you would do is you type in your 6, go to your math menu, arrow over to PRB for probability, and number 4. So you can either type number 4 or you can arrow down to number 4 and press enter, and that will put the factorial on your number for you. Press enter again, and it'll display the answer. So if the number is small, you might just feel like typing in, 5 times 4 times 3 times 2 times 1. But for larger numbers or more complicated expressions, you might use your factorial function in your calculator. Okay, so let's take a look at B. 8 factorial times 3 factorial. So I would type my 8 in, math, PRB, number 4, and then 3 factorial. And you can, if you want to, put the times, the multiplication symbol between them, but you don't have to. Your calculator will know what to do. So that gives us 24,000, or no, 241,000. 920. Okay, C. I'm going to show you how to do this one by hand, and I'll let you check it on your calculator. So we have 10 factorial divided by 5 factorial. Let me mention that this is not 10 divided by 5 and then a factorial. So if you write down 2 factorial, that is not how you do this. What you could do is say 10 times 9 times 8 times 7 times 6 times 5 factorial. Now I could write down 5 times 4 times 3 times 2 times 1, but I know that it keeps going down from 5, so I just leave it at 5 factorial. Well, notice what happens when I leave it like that. The 5 factorials cancel out, and so I'm just left with 10 times 9 times 8 times 7 times 6, which gives us 30,240. So if you were to divide, you'd get the same thing, but just be careful. It's not 10 divided by 5 and then a factorial. So it's not 2 factorial, but 10 factorial divided by 5 factorial. On D, notice that the factorial is outside of the parentheses, so we would do 12 minus 5 factorial here. So that we would do 12 minus 5 first, and then do the factorial. So this would be 7 factorial, or 5,040. And E, quite a lot going on there. Again, you can do that one on your calculator, or you can kind of do this canceling stuff. Well, 10 factorial, I know would be 10 times 9 times 8 times 7. So I'm just going to factor out the 10 and say 9 factorial. And I'm going to leave the 6 factorial alone. But that 9 factorial is going to cancel out, so I'll leave that there. But for the 7 factorial, I can break that down into 7 times 6 factorial. And notice that 6 factorials are going to cancel out, and 9 factorials are going to cancel out. So that leaves me with 10 over 7. So it's up to you if you want to use your calculator on that one, but sometimes by the time you do all the punching in, you might have been able to kind of figure it out by hand and not have to do so much work. Okay, example 6. 20 contestants are competing in a talent show where prizes will be awarded to the first 5 places. How many ways can the contestants place? So again, I'm going to think of my slots. 5 places. And there's 20 contestants competing. So in that first slot, there's 20 different people that could be first place. But once I choose the first place contestant, then there's 19 that could be in second place, and then 18 in third place, 17 in the fourth place, and 16 in the fifth place. So this almost looks like a factorial, but we don't go all the way down to 1. Let's see what we get here. 20 times 19. $1,860,480. So we had a descending product of integers just like with our factorial, but we didn't make it all the way down to 1 this time. We didn't go 15, 14, 13 all the way down to 1. So to show that we chose from 20 objects, the contestants, but we only took them 5 at a time, the arranged 5 places, we used what's called a permutation. Okay. So the number of possible arrangements if R items are taken from N items is, we use this notation NPR. So N is the number of objects I have all together, and I'm taking a group of R of them. So in this case, we had the 20 contestants, and we took 5 of them to 5 places. The way you calculate that is N factorial over N minus R factorial. So let's just look at that back here with the problem we already did. So if I were to write this in permutation notation, I would say 20 P5, and I would set that up as 20 factorial divided by 20 minus 5 factorial. Notice my factorial is on the outside. Well, that ends up being 20 factorial over 15 factorial. And if we cancel, kind of like we've been doing before, we end up with exactly what we did in the first place. We only went up to 16. So that's how that permutation notation works. Okay, now let's try example 7. An organization has a total of 29 members. 3 members will be selected to the offices of President, Vice President, and Treasurer. Assuming all members are eligible to serve in each office, how many arrangements of the offices can be made? Well, we have 29 objects, 29 members, and 3 offices. So this is going to be 29 P3. So I would set this up as 29 factorial over 29 minus 3 factorial. So that's 29 factorial over 26 factorial. So that means 29 times 27 times 20. Hold on. 8, 20, going to cancel here. So all I have to worry about is 29 times 28 times 27, which gives me 21,924. Okay, so let me show you a shortcut on your calculator how you can do that, because your calculator actually has this function built in. Now notice the 29 came first, and then the P, and then the 3. So if I type in 29, go to Math, go to that same PRB or probability menu, and the second choice in PR, that's your permutation. Press Enter, and it's going to display NPR, and then type in the 3, which is the second letter. So what this is doing is setting up 29 as N and 3 as R. If you press Enter, you get the same answer. Okay, example 8. Consider the organization from example 7. So the 29 members, and we were going to elect 3 officers. Instead of electing officers, the organization decides instead to just have a leadership committee made up of 3 members. How many ways can members be selected for the leadership committee? Well, now this is a little bit different because I don't have special offices that I need to elect to. Before we actually get into the calculation of this, let's talk about what a combination is. I think that might be a little easier to understand. So in example 7, we had distinct places, a president, a vice president, and a treasurer. Now we just have a committee, and there's no distinction among the 3 people who will be chosen. So that changes things a little bit. So because of the committee, order no longer matters. In example 7, it absolutely did, because even if it were the same 3 people, even if it was Mary, Bob, and Jim, Mary being president and Bob being vice president and Jim being the treasurer is completely different from Jim being the president, Mary being the vice president, and Bob being the treasurer. Even though it would be the same 3 people, because they would be in different offices, the order matters. Whereas if Mary, Jim, and Bob are on a committee, we don't care about the order because they're just all on a committee. And so that distinction of order determines whether we have a permutation or a combination. And here with the committee, the order does not matter. So this is a combination. Now for a combination, our little formula changes a little bit. This is still R items taken in at a time. So notice our letter here changed from a P to a C. So in NCR, we have n factorial, n minus r factorial, but we have this extra term added here, r factorial also. And what this really does is take the permutation and we're dividing out all the repeats. So ABC means the same thing as CBA in a combination because now order no longer matters. So let's go back to this example 8. So we still have the 29 members we're choosing from, but this time it's a combination instead of a permutation because order does not matter, and we're selecting 3 people. So if we use our formula here, that's 29 factorial divided by 29 minus 3 factorial and 3 factorial. So that's 29 factorial divided by 26 factorial and 3 factorial. We know that 26 is going to cancel out. So 29, 28, 27, and then 20. So just type in 29 times 28 times 27 divided by, well, I know 3 times 2 times 1 is 6. So this is 3,654. Well, just like before, you can do the whole thing on your calculator. I would type in 29 first, go to Math, PRB, number 3 for combination, type my 3 behind that, and I get the same thing. Okay, so in example 9, I've kind of mixed it up here. We have to decide whether the situation presented is a combination or a permutation. So the main question you're asking yourself is, does order matter? So let's take a look. A, for a segment of a radio program, a DJ can play 7 songs. If there are 13 songs to choose from, in how many ways can the program for this segment be arranged? Well, order will matter here. The order of the songs is going to matter. So A is a permutation. And I can set this up as 13 songs to choose from, P7. That's 13 factorial over 13 minus 7 factorial, or 13 factorial over 6 factorial. So I could do this as, oh, I think I'll do it the easy way. So I could just say 13 P7, and that gives me 8648640. So 8,648,640. Okay, B. In how many ways can a police department arrange 8 suspects in a police lineup if each lineup contains all 8 people? Well, order matters here. The different arrangements are, one guy being first versus being second or third, that's going to matter. So this is another permutation. And we can set this up as 8P8. What I want you to notice here is if I use my formula, that'd be 8 factorial over 8 minus 8 factorial, which is 8 factorial over 0 factorial. Remember, we said 0 factorial is 1, so we just get 8 factorial. So what I want you to notice here, this is still a permutation, but if I use all of the objects presented to me, then it just goes back to a factorial. So I could just do 8 factorial, and that's equal to 40,320. Okay, and C. There are 14 standbys who hope to get seats on a flight, but only 6 seats are available on the plane. How many different ways can the 6 people be selected? Well, if you've ever flown standby, all you care about is that you get on the plane. It doesn't matter whether your name is first or second or last, just as long as you're in it. So this is the 6, and on my calculator, that would be 3,003. Finally, in example 10, in the Arkansas Scholarship Lottery Powerball game, players can choose 5 numbers from 1 to 59. If they match the numbers drawn, then the prize is $200,000. How many different selections are possible? Well, first ask yourself, is this a combination or a permutation? Well, it doesn't matter how you choose those numbers, which one you choose first, as long as they match. So this is definitely a combination. We have 59 numbers to choose from, and we're supposed to choose 5 of them. Something tells me this is going to be a pretty big number. Okay. So there's over 5 million combinations that are possible. So knowing that, what's the probability of matching all 5 numbers? Well, only one combination is going to match, so the probability of matching all 5 would be 1 over 5,006,386. It's just very, very small. This is 6 zeros. Remember that e to the negative 7 is really scientific notation? That's an astronomically small chance of matching. Okay, so if you think that's bad, take a look at this. Additionally, players are asked to select a Powerball number from 1 to 39. If this number matches along with the 5 selected numbers, then the player wins the jackpot valued at approximately $20 million. How many different selections are possible with the Powerball? Okay, so I know just the 5 numbers is, the number of ways to do that is 5,300. I want to choose one number from 39, choose 1. So what do I do with that 39 and the 5 million? You actually multiply those two together. So that's 39 times 5,386, or 6,386, which makes it now 195,249,054 different ways. So now what are the odds for winning? Well, if you recall how we do odds, first the probability of winning would be 1 over that large number. And the probability of not winning, the complement, would be 195,249,053 over 195,249,053. So to set up the odds for winning, so that would be 1 over 195,249,054 over 195,249,053 over 195,249,054. This should be a 4. 054. Remember that we can cancel our denominators rather. Oh goodness. So this is 1,2,1,95,249,054. So you've heard the term 1 in a million. This is 1 in 100 million, almost 200 million chance of winning the lottery. So, very small chance. I know some people still enjoy playing, and that's perfectly okay, but the odds are really stacked against you.